Good morning to everyone. Good morning to the Scientific Commission. My name is Alberto Portera and I am a PhD student at Politecnico di Torino. Today I'm going to present part of the research work that I have performed here at Politecnico. The title of this presentation is Investigating the Safety Benefit of Red LED Strips at Mid-Block Crosswalks under Distracted Driving Conditions. First of all, let's start with some statistics. The World Health Organization reports more than 270,000 pedestrian fatalities in 2022, where the main causes are driver distraction, failure to comply with yielding rules, overspeeding, etc. Authorities and institutions are trying to reduce this number, trying to implement and install some countermeasures in our road. Nowadays, the smart road technologies have been considered as a good countermeasure to increase the level of safety and increase the sustainability of the entire road network. At mid-block crosswalks, several smart road technologies have been proposed and installed, but only few studies examined their impact on driver behavior and safety, while most of them are just concept and no evident scientific results are available on the effects of these technologies on driver behavior and safety. Moreover, no one examined the potential benefit of these technologies in mitigating driver distraction. That is the primary cause of accident of pedestrians. This study aims to fill the gap in knowledge regarding the effectiveness of smart crosswalks under distracted driving conditions using a driving simulator. The technology that we proposed is made of two red LED strips that turned on when the pedestrian stepped inside the crossing area, while they turned off when the pedestrian left the crossing area. We decided to use the red because in the literature is the color that conveys most dangerous. About the experiment, we designed a 2x2 factorial experiment in which the first factor was the type of crosswalk. We used two levels in our scenarios we put conventional crosswalks where only the zebra crosswalk was present, while in the second level we used the smart crosswalk with the technology that I described before. The second factor was the not driving related task that we used as a variable to replicate cognitive distraction. We used two different levels, the low complexity in which participants were asked to perform some summations with two-digit pairs of numbers without regrouping, while the high complexity task required summation functions with two-digit pair of numbers, in this case with regrouping plus a memory task. In the memory task, participants were asked to remember a number that was provided in the previous summation. About the scenario, we designed 4 different scenarios to replicate the combination of the experimental factor. We involved 36 participants between males and females with different ages, and we performed a within-subject design. In each scenario, we considered 3 experimental crosswalks to investigate our experimental conditions, while our other 3 crosswalks were put in order to confound the participant and to avoid him or her to understand which could be the experimental crosswalk and which one is not. The order of the crossing has been fully counterbalanced to control the order and the learning effect. The posted speed limit was 50 km per hour, since it was a urban scenario. In the experimental crosswalk, the pedestrian was hidden by the presence of a car parked in the vicinity of the crosswalk, and the crossing started always from the right side. Finally, the cognitive distraction started 200 meters before the crosswalk and ended after the crosswalk. Let's see now the main result. The first variable that we analyzed was the speed at the brake pedal pressure, that corresponds at the speed when the driver reacted for the first time at the presence of the pedestrian. What we can see is that the configuration of the crosswalk had a minimal impact on speed maintained by drivers, and the statistical provided no significant differences. While what we can see is the complexity of the not driving related task influenced significantly the speed of participants, prompting drivers to adopt a more cautious approach when faced with the high complexity task. And what we can see is that the speed decreased for both in conventional and smart crosswalk when the high complexity was provided. About the reaction distances, we measured the reaction distance at brake pedal pressure. What we found is that the implementation of the smart crosswalk enabled participants to react from a greater distance compared to the conventional crosswalk. So the reaction distance increased when the smart crosswalk was installed. While the increased complexity of the not driving related task required drivers to allocate more time for reaction, resulting in a shorter reaction distance in relation to the crosswalk, both for conventional and smart crosswalks. Another variable that we used was the minimum time to collision. Before going into the details of the result, I want just to explain for those that are not familiar the meaning of time to collision. The time to collision is the time remaining at a potential crash if the vehicle and the pedestrian in this case maintain the same trajectory and the same speed. While if one of the two entities provide an evasive maneuver, this crash will be avoided. As we can see from the video, the more the distance is between vehicle and pedestrian, moreover, the lower is the speed between vehicle and pedestrian, the time to collision is higher, and it means that this is a safe condition. While if the vehicle and the pedestrian are very close and the speeds are still high, the time to collisions decrease dramatically. What we measured in each interaction was the minimum time to collision. It means the minimum value of time to collision that we recorded in each interaction, that provides the measure of the severity of the interaction. Now let's analyze the results of the minimum time to collision. If we consider 3 seconds as a threshold that separates conflicts with undisturbed interaction, what we can see from this result is that the smart crosswalk resulted in a minimum time to collision higher than 3 seconds, prompting undisturbed interaction between vehicles and pedestrians. It means that with the smart crosswalk, the interaction was much more safer. Moreover, in the conventional crosswalk, the high not driving related task deteriorated the safety of vehicle-pedestrian interaction. While with the smart crosswalk, the high not driving related task didn't deteriorate the safety of the vehicle-pedestrian interaction. Finally, we have also results on subjective measurements. We use NASA Task Load Index as a variable to evaluate the subjective mental workload perceived by drivers during the simulations. What we found is that the manipulation of task complexity was effective in influencing driver mental workload. Participants reported a high mental workload when engaged in the high complexity task compared to the low complexity task. Moreover, the introduction of the smart crosswalk resulted in a slight reduction in participant mental workload. Here I summarize the main findings that we found in this research. The introduction of smart crosswalks led to earlier reaction by drivers, as indicated by longer reaction distances, highlighting the safety benefits associated with smart crosswalks. With smart crosswalks, the minimum time to collision values exceeded the threshold of 3 seconds, indicating undisturbed interaction between vehicles and pedestrians and ensuring safer interaction. Finally, the presence of a smart crosswalk can help mitigate the effect of distracted driving caused by engagement in a non-driving related task and allow drivers to react promptly. Thank you, everyone.